Chemistry. This lesson is on the subject of hybridization. So hybridization was developed by chemist Linus Pauling, who won Nobel Prizes for both chemistry and peace. Hybridization occurs during covalent bonding when two different energy levels, such as S and P, combine to form a mixed energy level that is somewhere between the S and P levels. Pauling came up with the idea of hybridization when he compared the alpha structure of carbon with the bonding of CH4, methane. Hybridized energy levels occur only when two or more atoms are covalently bonded. If the bond is broken, the hybridized energy levels will disappear. So hybridized means to mix two things, like mixing apple and orange juice. We can hybridize S and P subshells to form hybridized orbitals. If we mix the 2s and 2px subshells together, we get two sp1 hybrid orbitals. The superscript 1 means that 1p subshell was used. The 2py and 2pz subshells remain unhybridized and can form double and triple bonds. We'll discuss that later. So here's what would happen if you mix the 2s and the 2px. This would happen. They would both blend and they'd form two sp1 subshells. And those two would be halfway between the original S subshell and the P subshell. So since they're half S and half P, they're going to have the energy level that's halfway between the two. sp1 hybrid energy levels are halfway between the S and P energy levels. If we mix the 2s, 2px, and 2py subshells together, we get three sp2 hybrid orbitals. The subscript 2 means that two p subshells were used, the px and py. So watch what happens when we do that. Okay. The 2pz subshell remains unhybridized and can form a double bond. We'll discuss that later. But the sp2 hybrid energy levels are 2/3 of the way between the S and P energy levels because they contain one S and two Ps. If we mix all three of the P's, the 2s, 2px, 2py, and 2pz subshells together, we get four sp3 hybrid orbitals. The superscript 3 means that three p subshells were used. So watch what happens. Since there are no unhybridized p sections, sp3 hybrid energy levels can form only single bonds. So this is what the result will be. sp3 hybrid energy levels are 3/4 of the way between the S and P energy levels because they consist of one S and three P subshells. The alpha structure for carbon is the following. In creating a CH bond, the alpha structure for carbon shows only two places where hydrogen atoms could share electrons to form covalent bonds. That's those two empty spaces in the px and py. The structure for methane is shown below. CH4 requires places for four hydrogen atoms to share electrons. All four of the CH bonds also have equal energy. So there's a contradiction here somehow. The alpha structure for carbon is the following. There it is again. And the Lewis dot structure for carbon is shown below. And there it is. You've drawn that before. So the alpha structure for CH4 shows only two places, 2px and 2py, where the hydrogen atoms can bond. The CH4 requires places for four hydrogen atoms to share electrons, which are shown in the Lewis dot structure. Pauling needed to resolve this contradiction. His first hypothesis was to have one of the 2s electrons promoted to the 2pz. By doing so, he created four places for hydrogen to bond. So we take that electron, we move it up to there, and now you have four locations where the hydrogens could bond. Now a hydrogen atom could bond with each of the four second orbital sections to produce CH4. So that seemed like that might solve the problem. While this created 4 CH bonds, the bonds were not of equal strength. 3 of the bonds are formed with the 2p subshell and 1 with the 2s subshell, so they're not all the same energy. Pauling's measurements of CH4 bonds showed that all 4 were of equal strength, equal energy. Pauling reasoned that the S and P subshells must mix together to form 4 subshells that all had the same energy. Pauling reasoned that there needed to be a way to mix the 2s, 2px, 2py, and 2pz subshells to produce 4 bonds of equal strength. The 2ps, 2px, 2py, and 2pz produce 4 new hybrid orbitals of equal energy. The hybrid orbitals are labeled sp3 because they are created from an s section and 3 p sections. So there you see the original 2 second orbital energy levels. And what will happen is this: they will mix, and you will get a 2sp3, another one, you'll get 4 altogether, and they're all of equal energy, 3/4 of the way up from the S subshell to the P subshell. Since there are 3 P sections and 1 S section, the energy level of the 4 hybrid sections is 3/4 of the distance up from the 2S to the 2P energy level. The word hybrid means to combine 2 or more things into one. For example, a hybrid car combines a gas-powered car and an electric-powered car. The new sp3 orbitals were 3/4 2p subshell and 1/4 2s subshell. All 4 were of equal energy and unpaired so that 4 H atoms could form 4 single bonds of equal energy. And so now you see how they come in and they form those 4 bonds, CH bonds of equal energy. Looks like that. So the 1s2 orbital is inside the valence second orbital and does not play any role in the bonding. So hybridization provides an adequate hypothesis for the existence of 4 equal energy levels. For this lesson, the orientation of Px, Py, and Pz will be shown as below. So the Px goes left to right, Py is forward out of the screen and back, and the Pz is up and down. The x-axis will be the axis between the 2 bonding atoms, and that is called the internuclear axis. The following are the rules for hybridization. 1. Draw the Lewis dot structure for the molecule. 2. Determine the number of electron domains. 3. Determine the hybridization based on the table below. And 4. The number of hybrid subshells will equal the original number of electron domains. So if you have 2 electron domains, and you can look at your VSEPR sheet for this, you're going to use that same sheet for this lesson. The hybridized form would be SPX. The hybridization is SP1, or it's usually just written SP. And that means you're going to have 2 hybrid subshells, the same number as the original number of subshells, a S and a PX. 3, okay, that's going to be S, PX, PY. You're blending those together into 3 hybrid subshells. So that's called SP2, and that gives you 3 hybrid subshells. 4 is going to be S, PX, PY, PZ. That was like the CH4 that we saw earlier. And that's SP3, and that will give you 4 hybrid subshells. Now when we go into the extended octet, you have 5 electron domains. That would be S, PX, PY, PZ, and one of the D sections, DXY. We said that's where those extra electrons went, was into a D, into the D orbital, the D subshell. That would be sp3d, and that would have 5 hybrid subshells. Then 6, okay, 5 would be the trigonal bipyramidal, and 6 is the octahedral. That would be S, PX, PY, PZ, DXY, DXZ. So that would form 6 sp3 d2 hybrid orbitals, and that would be 6 hybrid subshells. Now, the sp and only sp can form double and triple bonds. It doesn't have to, but it has 2 unhybridized p sections, and therefore it can form a double and a triple bond. sp2 hybridization can form double bonds only. That's because it has 1 unhybridized p section, and that would be the pz. So it can form a double bond. Now, the 5 and 6 domains, that would be the trigonal bipyramidal and the octahedral when it comes to geometry. Note that the AP tests on VSEPR geometries of extended octets, but does not test on the hybridization of these electron domains. So you won't see the sp3d or sp3d2 tested on the AP exam. You will, however, be expected to know trigonal bipyramidal and octahedral geometries. So hybridization is determined by the number of electron domains an atom has. So we're going to do a little practice here. Oxygen has 3 electron domains. 1 is a bonding domain, and 2 are non-bonding domains. That means lone pairs. But because it has 3 electron domains, it has an sp2 hybridization. Carbon has 2 electron domains. Both are bonding domains. This produces an sp hybridization. The oxygen on the right, same as the left. Oxygen has 3 electron domains, 1 bonding domain, and 2 non-bonding. This produces sp2. Just remember, if it's 3 electron domains, it's going to be 3 letters. S, PX, PY. So that's 3 letters. And it's sp2, which is 3 hybrid subshells. Over here, hydrogen does not have a p subshell, so it does not hybridize. Carbon here has 2 electron domains. Both are bonding domains. This produces an sp1 or just sp hybrid. And notice here that sp has 2 unhybridized p subshells, which can form double or triple bonds, and in this case, it does form a triple bond. Now, nitrogen has 2 electron domains, 1 bonding, 1 non-bonding, so this produces 2 sp hybrids. And again, an sp has 2 unhybridized p sections, a py and a pz, which can form triple bonds, and here they formed a triple bond with the nitrogen. Steric number. A couple of notes here. An alternate name for electron domain is steric number. If an atom has 3 electron domains, it has a steric number of 3. So those two terms can be used interchangeably, electron domain and steric number. VSEPR and hybridization. So there can be some confusion between the two. So VSEPR applies electron domains and bonding domains to the central atom only to determine the geometric shape of the molecule. The terminal outside atoms play no role in the geometric shape. Geometries are determined by the ax notation of the central atom. Hybridization can be determined for any atom in a molecule to determine the energy levels in a covalently bonded atom. Hybridizations are designated as sp, sp2, sp3, and sp4. Hydrogen has no p subshell and does not hybridize. Okay, if an atom has 2 electron domains created from 2 bonding domains or 1 bonding and 1 lone pair, the 2s and 2px will hybridize to an sp subshell, actually to 2 sp subshells. So there you see the 2 sp subshells, and those are shown over on the right, and those are the one that they're both on the internuclear axis, one pointing toward the other atom and one pointing away. And then you have the 2 unhybridized py and pz. Those are the red and blue sections that you see there, and they can form double or triple bonds. So the unhybridized py subshell can form a double bond, and the unhybridized PZ subshell can form a triple bond. The Lewis dot structure will determine whether a double or triple bond is created. It does not have to be in every case. If an atom has 3 electron domains, 2s, 2px, 2py, will hybridize to an sp2 subshell. The 3 sections, 2s, 2px, and 2py, create 3 sp2 sections. So there you see in gray there, you have 3 sections there that are sp2. Notice they form a trigonal planar geometry, and that's from your Vesper sheet. And then the one unhybridized, the pz, can form a double bond. So there you see what the alpha would look like. You have 2 sp2 3 times, and they're 2/3 of the way up from the s to the p, and and then there's one 2pz, and that unhybridized pz can form a double bond. Okay, if an atom has 4 electron domains, 2s, 2px, 2py, 2pz, will hybridize to 4 sp3 subshells. That was like CH4. The 4 sections create 4 sp3 sections. So there they are, and they're all of equal energy strength, such as in CH4. sp3 hybridization leaves no unhybridized p sections, so there can be no double or triple bonds. So here's a summary. When we began this course, we learned that atoms have energy levels in which electrons travel called orbitals. Orbitals are numbered 1, 2, 3, 4, 5, 6, and 7. Later we learned that orbitals are further divided into subshells S, P, D, and F within these orbitals. For example, the 2p subshell is higher than the 2s, but lower than the 3s. Now we have learned that S and P subshells can be further divided by hybridization. The main difference is that hybridized orbitals occur only when atoms are covalently bonded into molecules. The sp, sp2, and sp3 hybridization levels appear when the energy levels of 2 or more covalently bonded atoms are blended into energy levels between S and P. If the bonds are broken, the hybridized energy levels will disappear. Okay, so that takes care of this lesson on hybridization. And so when you practice this, you'll see how it relates to Vesper and how it's different from the Vesper notations.